This is a video abstract for our article entitled Bioverse, a comprehensive assessment of the capabilities of extremely large telescopes to probe Earth-like O2 levels in nearby transiting habitable zone exoplanets, by Kevin Hardegree-Ullman, Dániel Apai, Galen Bergsten, Ilaria Pascucci, and Mercedes López-Morales. Published in June 2023 in the Astronomical Journal. The search for life beyond Earth is a major driving force for exoplanet research. Beyond the solar system, we can search for biosignatures such as oxygen, methane, and carbon dioxide in the atmospheres of Earth-sized exoplanets orbiting within the habitable zones of their host stars. One potential method to detect these biosignatures is transmission spectroscopy, probing the atmosphere of an exoplanet as it transits in front of its parent star. Molecular oxygen, O2, is a key biosignature since it is generated from the biological process of photosynthesis on Earth. In our study, we explored if it would be possible to probe present-day Earth-like levels of O2 on an Earth analog using upcoming extremely large telescopes, ELTs, coupled with high-resolution spectrographs such as the Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope. Since the ELTs will observe through Earth's O2-rich atmosphere, relative system velocity at the time of transit observations is an important consideration to mitigate the effect of line blending. This visualization shows part of the O2 A-band at a spectroscopic resolution of 100,000. The top panel shows how an ideal Earth-like exoplanet transmission spectrum would appear at the listed relative system velocity. The middle panel shows Earth's telluric signal, and the bottom panel shows the combined signals compared to Earth's telluric spectrum. Severe line blending is illustrated by an orange combined spectrum. We expanded and improved upon previous studies on the subject of exoplanet O2 detection by using the Bioverse framework to simulate a survey of habitable zone Earth-sized planets orbiting stars within 20 parsecs of the Sun. In our simulations, we accounted for exoplanet occurrence rates, target observability, and importantly, relative system velocities at the time of observations. Our simulated survey results indicate that it would take about 100 years to probe Earth-like levels of O2 at 3 sigma significance on a typical nearby Earth-like planet via transmission spectroscopy if we can observe every single transit of that planet from each ELT and combine the signals. A more optimistic observing scenario in which we only require partial transits rather than full transits could reduce observing time to about 60 years. A higher resolution spectrograph at R equals 500,000 could further reduce that time by a factor of 2. Luckily, we have the TRAPPIST-1 system, which is a late-type M-dwarf at 12 parsecs with 3 or 4 transiting habitable zone Earth-sized planets. It is currently unknown how similar these planets are to Earth, or if they even have atmospheres, but if they do, Earth-like levels of O2 could be probed on these planets within 16 to 55 years with first-generation R equals 100,000 spectrographs on the ELTs in the partial transit observing scenario. Given the significant resources and time required to make a single O2 detection via transmission spectroscopy, it is unlikely ground-based telescopes will be used for this purpose unless more compelling targets are discovered. Transmission spectroscopy with the ELTs will still be a very fruitful endeavor, enabling exciting and crucial atmospheric studies of hundreds of exoplanets. The search for O2 with ELTs, however, will likely continue via direct imaging and reflected light spectroscopy.